and see if you can figure out the change in momentum. So idea here is being something happened, you've got an initial velocity and then it stops. Maybe it ran into like a bumper or something, or it crashed, okay, so it stopped. So there was a before the crash and after the crash. And so the change in momentum is always the after minus before, right? Final minus initial. It's initially moving to the left, and we've defined positive towards the right, so its initial velocity is negative 2 meters per second. It suddenly stops. What's the change in momentum? So it was 20, but it's plus 20, I think. One thing about the textbook is that they use what's called a prime, which I sometimes refer to as a ticky thing, half a quotation mark or something like that. So they say P is momentum before, and P prime, or P with the ticky thing, is momentum after. So the little primes go on the after the collision. But anyway, so idea is that before, it's moving to the left, so you'd say it's 10 times minus 2. So you get negative 20 kilograms meters per second. And then after P prime, it stopped, so it's 0. Okay, so that's before, that's after. And delta P is equal to P prime minus P. Okay. Change is always final minus initial. And that's equal to 0 minus negative 20. So the minus, you get a plus. You get delta P is equal to plus 20. And the units are kilograms times meters per second. The ball goes up at some time t2, it has a momentum. At some time t1 it has a momentum, then t2 it has another momentum. Neglect air resistance. How does the momentum of this ball compare at time t1 on the way up to time t2 on the way down? Momentum is the same or momentum is different? It's different, so that's what I was trying to get at here. So A was correct for kinetic energy, and it's also correct for the magnitude of the momentum. If you neglect air resistance, this thing has the same speed on the way up as way down. So this question is emphasizing the fact that momentum is a vector. Two ice skaters, Paula and Ricardo, push off from each other, and they were both initially at rest. Ricardo has a greater mass than Paula. I'm not really sure which one's which here. Which skater has the greater magnitude of the momentum after the push-off? Neither. Interesting. And this is what I was thinking, okay? I agree. I was thinking that maybe it should be Ricardo because it's more massive. But let's think about this next one actually, since we're on this. Let's do the same exact question now again. Two ice skaters, Paula and Ricardo, push off from each other. They were both initially at rest. So the initial momentum of this system in the horizontal direction was 0. And then they push off, and I would say that the final momentum of the system must still be 0. Meaning that if one of them has a negative momentum of some magnitude, the other one should have a positive momentum of the same magnitude. Equal and opposite momenta. They have the same magnitude but opposite direction, and that's why the conservation of momentum, 0 becomes 0. That's what we're going for here. So, now that you know that, momentum is the same. What does this mean for the velocities? So you have to invert this equation. P equals m over v, v equals p over m, I think, right? You got it. Okay, so here the concept is momentum. They were both initially at rest, so p is equal to 0. And then what happens here is that p prime of, I guess, Ricardo is, or the magnitude there is equal to the p prime of Paula. And so that way, p prime of Ricardo plus p prime of Paula still equals 0. So you get, that's the point there. And then what happens is that you do v is equal to p divided by m. And so it's the same magnitudes of the momentum, and so the more massive object travels slower. Okay, so we've got greater magnitudes from the less massive. Just imagine you're peacefully trapped in a canoe and you're in the middle of a lake and there's no paddles. But you do, for some reason, have a bag of rocks. The rocks are 10 kilograms, and maybe you in the canoe might be, 100 kilograms. Is it possible to get yourself moving? So you throw the rocks away from the shore, idea being your initial momentum of the system is 0. So if the shore is in the positive direction or something, and you give the rocks a negative momentum, then the remainder of the system, which is you and the paddle, or you and the boat, would have a positive momentum to compensate. And this is exactly how rockets work in outer space. There's nothing to push off of in outer space. So what they do is they just blast a lot of exhaust out of the rocket, and it's the momentum of the exhaust going in one direction that causes the rocket to just go in the other direction. It seems like a crazy way to do it, but it's the only way to travel in space. There's no such thing as warp drive from Star Trek, as it turns out. You can just do things by the laws of actual physics, which is this is it, away from the shore. During a head-on collision, how does an airbag protect a passenger in a car? A, it decreases the impulse exerted on the passenger. B, it decreases the initial momentum of the passenger. C, it lengthens the stopping time interval for the passenger and decreases the force exerted on them during the collision. Or D, it shortens the stopping time interval for the passenger and increases the force exerted on them. Okay, it lengthens the stopping time. And so you've got some fixed delta P because you were going at some initial speed, whatever speed you were going, but then you hit a tree, and the tree is at 0 speed. So you go from initial to 0, and you can then the passenger has to also go from initial to 0. You can either stop by hitting the steering wheel or the dashboard, which is made out of hard plastic, and that'll stop you in a short delta T with a large F net, or you can kind of slow down over a greater time. So you got this basketball, it's going down, we define X towards the right and Y to be up, and so its initial momentum just before it hits the ground is, its components are +5 and -5, so it's going at an angle of 45 degrees relative to the ground. Every time it bounces, it loses a little speed, so what's interesting is that if you do Pythagoras, you don't get the same speed before and after the collision. It's a little less. Thank you so much. So a lot of you said that there's 0 change in the x component of the momentum. Okay. So once again, with it's sort of like Newton's second law. It's really 2 Newton's second laws because it's a vector equation. This impulse is a vector. So it's a change in momentum that you have to resolve into components. This is the exact same question, but now it's asking you what's the change in the y component of the ball's momentum. I got, pretty good. So it's positive. I like that because the force from the floor on the ball is positive, right? So it should be changing its momentum in the upward direction. That's good. So let's see if I can work out the numbers here. This one was 0. For this one, you've got P final, so delta P is equal to P final minus P initial. So it's this mass times V final. So it's 0.1 times the V in the y direction, delta P y is 0.1 times V y final minus V final is +5 minus -4. 0.1 times -9. Oh, sorry. Yeah, +9, sorry. -4 is adding 4. So you get 5 + 4 plus 0.9 kilograms meters per second. So this is, I want you guys to do the prediction of a demonstration that John has set up here, in which I have 2 equal mass balls. One is made of rubber, and one is made of this clay putty. The thing the rubber one's already in its little position. But what I'm going to do is test to see if when I swing it down from a certain height, will it knock over this block of wood. 2 balls of the same mass, same speed, collide with a block of wood. One is made of putty and stops when it hits the block of wood. The other is made of rubber and bounces off. Which ball will deliver the larger impulse? I think he's got it set up so one knocks it over and the other doesn't. And we'll try it. See if we can get it going. So 67% are voting for the rubber ball, 18% are voting for the putty ball, and 15% are saying it doesn't make any difference. So let's give it a try. So this is the rubber we're going to try first, the bouncy ball. Okay, bouncy ball knocked it over. Okay. See if this one also knocks it. Oh, it doesn't. So there you go. So presumably the rubber ball exerted a larger impulse. I don't know if you guys like that or not, because it didn't bounce, right? All it did is stop. So when you bounce, there's twice as much impulse needed. It's kind of equal and opposite impulse on the ball from the wood and the wood on the, wood on the ball. But just bouncing takes twice the impulse is the concept here.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.